All right, hello, and welcome to, I suppose this is the fourth lecture for digital game design. This week we're going to be talking all about systems and how systems work within games and how games themselves are a system. Now, unlike a lot of systems, the goal of a game is not necessarily to create some kind of product or manufacture something. It's not there to simplify some kind of work process or perform tasks. Games are for entertainment, and so there's a little bit of nuance or interest in the way that these kinds of systems are created. In games, and if you remember back to last term, we have these formal and dramatic elements that work together. They create some kind of structured conflict that provides an entertaining process for players to then go and resolve. And so how that interaction of those formal and dramatic elements is actually structured is what forms the game's underlying system and really what determines the nature of the game and the nature of the experience that the players are going to have. So as we kind of dig into that, let's take a few steps back and go all the way back to the beginning and say, okay, well, what exactly are we talking about? Because, let's just define what a system is. And you can kind of look all over the place. In general, a system is just a set of elements that interact together that form some kind of cohesive whole. And that whole set of interacting elements has a common goal or a common purpose. And this is kind of a nebulous and malleable definition. There are a couple key parts here. But for us as game designers, our goal is to understand the basic principles of how systems work in order to control the quality of the interactions in our games, to control the way that the systems within the game actually grow, and how understand how those systems will be changing over time. And you can you can look all over the place within games for these, because systems exist anytime that you see some kind of complex behavior that emerges from the interaction of a bunch of kind of more discrete elements. Looking around the world, you can see the systems are mechanical, they're biological, they can be social, and there's all kinds of classifications for what falls under the umbrella of a system. And they can be very simple and they can be very complex. A stapler is a very simple example of a system. It's a bunch of separate parts that you use, and the purpose of that thing is to attach two pieces of paper or whatever together. Going towards the more complex side of systems, you can look at how governments function and how there are lots of different kind of individual people that form other kind of subsystems, if you will, that make that whole process work. We're not necessarily diving into governments today, but again, just to kind of contextualize all this for you. So, systems for us are elements that are interacting to produce some kind of common goal, and that certainly includes games as well. Games are a set of formalized elements that work together and create a dynamic experience for players to kind of engage with. And so we see that games themselves are systems. And in fact, there's systems of a bunch of other smaller systems that work together within that larger system of a game to produce results that feed into that system of the game itself. And so really, games are just systems all the way down. So that's really why we care and why we need to understand how to interact with and design these sorts of things. So, thinking about games as systems and systems in general, systems can produce all different kinds of results. Some systems, the results are very precise and predictable. In other cases, some systems have really varied and very unpredictable results. And this really depends on what makes them up, how many different elements there are, how many different possible interactions there are. And there's a lot that can kind of go into that. Games use both of these. Certainly, at a very high level, you can think of one of the upper layers of systems in a game as being a very predictable system that only has a few possible outcomes. in this example, you can say we can win the game or lose the game based on a bunch of different things that interact as we play, or as a player plays. On the other hand, these more unpredictable systems can have lots of different outcomes depending on what the player is doing and how the player chooses to interact with it. And so you can kind of look at the moral choice systems within games for this. But one good example of a system that has a lot of moving parts and to the naive player is very unpredictable within the bounds of reasoning is kind of the final mission in Mass Effect 2, and that game calls it the suicide mission. And in that mission, there's a bunch of different choices that the player is asked to make based on the characters that are in their squad, who they've interacted with throughout the game, and so on. So the choices can range from, who goes exploring in the vents to look for an alternative way in, or who's exploring the vents to turn off the gas. I forget exactly what the specific is, but I know there's a vent choice. There's also a portion where your squad gets ambushed, and you as the commander have to choose who stays back to kind of defend and cover everyone's retreat. And based on how you've interacted with the game and the choices that you make, there are a lot of different outcomes. There's a great number of squad members. All these squad members have kind of individual quests that you can complete in order to make them trust you. And so all of those different things play a part. You have this diagram in your lecture notes, so I'm not going to break it all the way down right now, but just to give you a high-level overlook and maybe spoil some of the outcomes from Mass Effect 2, so fair warning, I guess. But this is what that choice system actually looks like. This is a flowchart of all the choices that a player can make within the scope of that one mission, and the outcomes based on each. Some of these are based on rules, some of them are based on chance, some of them are based on a mix of the two things. But kind of what you're seeing here is the three different stages of the mission: the approach, the base, and the end game. All of the elements on the left side are choices that players are making, and then we can follow those choices through to their results. Ultimately, noted here in the slide are, we have green boxes and red boxes, generally denoting that green is a positive outcome and red is a negative one. So again, if you are very interested in how some of those complex decision-making systems work, have a read through this, especially if you haven't played Mass Effect 2, and maybe, again, if you're not familiar with the game, watch a video of this mission to kind of get a feel for what that looks like. But not all systems are necessarily this complex, but it's a good example for the kind of depth that controlling and understanding how to control our systems can actually give us. So that's really why we're here this week, is that understanding systems and how those systems interact with each other give you a much finer element of control over the way that your games are played. And so we have to go, again, kind of back to the beginning before we get super excited about this and say, okay, well, I know what a system is, but what is a system made of? How do we build a system? And through that, how do we understand or determine how the system is going to act once we start the game? And so really the question we're asking is, what are the very, very basic components that we use to fit these much more complex things together? Kind of like going back to thinking about games as a whole and like what those really basic, like formal and dramatic elements are. There's kind of a similar approach to the way that we can think about systems. And systems really have four basic elements, and they all build on top of one another, which is great and fantastic. So we have objects, we have properties of those objects, we have the behaviors that objects can do, and the relationships between different objects within the system. And all of these things coming together give you an idea of how that system is going to act in motion. So how changes within the system are actually manifested really depend on the nature of those different objects and the ways that they interact. So at a very, very high level, We say systems are objects that interact with each other according to the properties of those objects. According to the properties of the objects, the behaviors of the objects, and the relationships to other objects. And all of these things will cause changes within the system either automatically or as they are acted on. Again, how those changes in the system manifest depend on the actions and interactions. Sorry, I was a slide ahead of myself. But like games, a lot of systems with a bunch of different parts create an opportunity for a lot of possible interactions and a lot of possible outcomes. And so I'm going to sidestep just a little bit because possibility is something that is extremely important to games and players, and something that I think is worth kind of touching on a little bit more deeply. Systems are what we call possibility spaces. There's room within a system for lots of different interactions and outcomes, as mentioned. Within games, we have players experiencing at any given time that sense of possibility. And possibility is extremely important to games. Whether you're simply presenting the actions that a player can do, or whether a player is making those moment-to-moment gameplay decisions and kind of defining the way that their own possibility plays out. So for us as designers, it's our job to basically present situations to players that are equal to their abilities, but also that grow in challenge over time. And this is going to come back to flow, which I believe you have an understanding of and we'll touch on a little bit later in the course. Now, possibility spaces are great, and I mean, if you've played like Minecraft, Terraria, or any of those like really big open world games, you know that possibility can be a really cool thing for players to play around in. I will say, and it's worth noting, that a lot of very, very successful games have very constrained possibilities. More possibilities does not always mean better. So, you know, when it comes to the range or type of different possibilities that your game provides, you need to be thinking not just about adding more and more of these things. You need to be making sure that your possibilities are, again, still driving forward with that intended experience that you want your gameplay to deliver. And you can think about some similarities between possibilities if you just look at the way that narrative or gameplay is structured in games that maybe you're familiar with. Certainly there are linear applications where, you know, we have like small spaces for possibility. This isn't just like a go to point A, go to point B, but there's like a space where players can make a limited amount of choices and experience in their own way, and then kind of travel linearly to the next sort of somewhat structured possibility space. In other games that have, you know, different potential outcomes, you can still see that there are some branching paths, and, you know, there's definitely more possibilities here because from the first area or level or whatever you might want to call this, there are a couple different directions that we can go. But keep in mind that as these kinds of branching possibilities happen in games, this is like more assets, more animations, and more work that your development team needs to be doing. So typically when we see these in games, they're even like as far as how many branches along the path are possible, they're still quite limited, despite, you know, trying to get the player to feel as though there are an endless number of possibilities, let's say. So, you know, sometimes, and I guess what I've got here is a couple different examples. This is a very small game from a while ago, but when we think about small ranges of possibilities, this is Proteus, but you could think of, you know, any kind of like adventure game that might have branching structures but does have a limited number of outcomes. In this game, Proteus, a player is kind of like dropped on a large landmass, and they kind of wander around and find a white rabbit and follow it. and then that leads to like the next area where they do the same thing until the game ends. There's no conflict or anything here. So within these kind of more constrained possibility spaces, when you're playing these kinds of games, or when players are playing these kinds of games, the challenge from the game and a lot of the core parts of that experience come from navigating those defined sets of possibilities. And so again, a lot of single player experiences follow this general path. Is there's a bit of possibility, and then there's kind of like a bottleneck where the player experiences some story or a cutscene or something, and then there's other gameplay possibility space. So there's still a lot that can be done here. On the other hand, when we think about large systems with lots of possibilities, you might be looking at something like The Sims. So in this case, much larger possibility space than something like Proteus or an adventure game. The way that this is usually done is simply just introducing more objects into the system with defined relationships to each other, of course. So these are games like The Sims. Real-time strategy games often have a lot of possibility built in. Look at like StarCraft, and of course MMOs all have the same kind of approach of just like there are a lot of different things related to a lot of different other things. And the difference, I suppose, is that the desired effects from larger possibility spaces are really that we are giving a greater scope of choice for the player, giving them opportunities for creative solutions to in-game problems, and depending on how the game plays out, this can also lead to enhanced replayability if there's like more than one viable possible way to play the game from beginning to end. And Sims is a good example because there are a lot of different ways to play The Sims and still be successful. Whether that is defined by in-game success or simply player satisfaction, as a lot of people do play The Sims. Some people play it for controlling the lives of the Sims and getting them to do interesting things. Some people play The Sims to like build interesting houses, and so on and so forth. And so there's a lot of, as I said, possibility here. So let's step back in. This is why we care about systems, the size of systems, controlling systems, and understanding how they all work. So back to those basic system elements, and let's kind of break them down. We've got, remember, objects, properties, behaviors, and relationships. Objects are the simplest, so we're going to start there. Objects are basically the basic system building blocks. They can be physical things like game objects, they can be abstract things like the rules themselves, or they can be a mix of both. And excuse me, that depends on the nature of the system that you're designing. These objects are then defined by their properties and their behaviors and their relationships with other objects. So they're kind of the root of this way of thinking about systems. So you've got your game objects or your pieces of the game, your models, in-game concepts, so lore, worlds, the players themselves, the characters that are representations of the players, all the way down to like the different areas and the terrain in games as well. The areas or terrain, whether it's like squares on a grid board or like I'm headed to sports for some reason, but like yardage on a play field, tracks in a race, all these things are objects. And so as we go through defining all of these things and learning a bit more about each of their components, we'll actually be building a system through the slides as well. So excuse my terrible PowerPoint art, but let's start just plopping some objects down. So I've taken 3. You can take as many as you like, but in the interest of time, I've got 3 because I don't want I know what I'm building and I want it to fit in a lecture. So I've got a human, a monster, and a sword, all in stunning HD. So don't worry about this. This is not interesting yet. We will come back to it and start adding stuff to it. Because right now, this is not a system. But it will be. We'll get there. So with objects covered, let's move to properties. Properties are just the qualities or the attributes that will define objects. So they can be their physical characteristics, they can be conceptual things, but really this is just properties are like a set of values. And so if you're more keen on the programming side and you're like, design might not really be for me, this lecture is for you, because sets of values and properties for objects is just like what goes into your code as you're building stuff out. And these are sure, it can be something simple as like height, weight, type of object, like it's a sword, great. But it can also be I've lost my train of thought for a second, but it can also be like the texture that's applied to that object. It can be the sprite that you're using, the animation, and so on. But really just properties form this set of descriptive data that is really what forms the basis for how objects will interact with each other. And like I've kind of alluded to earlier in the lecture, the more complex an object is, so the more different properties it might have, the less predictable that object is going to be. It might react in different ways based on those properties. But as I said, that's a little bit ahead of where we are. We'll get there. So complex objects have lots of properties. Really simple objects have very few properties and are much more predictable, let's say. Now, as you may have guessed, based on the way that we've been talking about this, some properties will change through gameplay. So this is pretty simple. You're playing an RPG, you level up, your character's hit points change. Simple. Maybe if you have a weapon in a game that is cursed, maybe there's a quest that the player can go through that removes the curse from that object. And of course, the more you start piling onto these objects, the more complex and unpredictable, and the more complex and unpredictable they become, and the more different possibilities they start to be able to present within the system. Pick your favorite game that features combat, and an easy place to find properties is within their weapons. So one of these two screenshots is CSGO, I think, or it could be old Counter-Strike, I'm not sure. But you can, paint a gun on anything and it's a shooting game. But let's pretend for a moment that we're talking about Counter-Strike Go somewhere here. Sorry. Anyway, these weapons have all kinds of different properties. So they have cost, they have ammunition, including how much ammunition they can use before they have to be reloaded. They have accuracy, they have fire rates, and in the case of this screenshot here, this information is presented to the player in a way that abstracts some of that information into a line. But for us as designers, we might have much finer control over the actual values of those properties. But it's not just properties tied to things like weaponry and things that players are doing for combat. If you think back to the Little Big Planet series, the terrain, again, kind of jumping on that as an object, also has really interesting properties. Certainly, as far as like level design goes, any piece of terrain has a size, has a texture or a material. But in Little Big Planet, this gets interesting because some of the materials that the level is made out of, the character can carry or drag or grab onto. Some pieces of terrain damage the player. Some pieces of terrain move, and kind of like how or when they move can also fit within, I guess that's kind of getting into behaviors, but certainly the ability to move is where we'll start with that. So let's go back to our system, and we'll give those objects some, a set of properties. So if I go back here, you see, again, my stunning HD art. My human now has some health. They have some strength and some defense. The sword has a number for attack. It's also got the property that it is two-handed, which once we define the relationships between all of these things, two-handed might become important. It has a texture that I've just called sword.png. So that's a property on that object as well. And a monster similar to my human also has some health, some strength, and some defense. Still not a system, but we're getting closer. Next up are behaviors. Behaviors is really what it says on the tin, right? Behaviors are the actions that an object might perform in a given state. And just like with properties, the more behaviors something has, the less predictable it becomes. And behaviors is where you start seeing those interactions with the rules of a game, right? So if I kind of step back to my other slide, a good example of this is, that heavier weaponry, heavy swords can only be equipped in two hands instead of one. Fairly simple. And so again, we can throw more and more behaviors at and between objects, and that increases the possibilities and the complexity of gameplay. Doesn't always mean a more enjoyable experience. Sometimes it does mean a lot more work. But again, understanding how your system grows in complexity and understanding how to control that is an important part of this process. Looking at what behaviors are, good examples are any kind of basic AI in games. Typically, and this is a topic for outside of the design scope, but a lot of enemies in games have a couple different states that they will use based on some kind of rules. So if nothing else is happening, that enemy will probably patrol, which is just a behavior where they move around some kind of set path if the player hasn't been detected. However, if that enemy has seen the player or has detected the player in some way, maybe they've heard the player, I don't know. If that player has been detected, but the enemy can't attack the player because they're too far away, then its behavior becomes, okay, I know where the player is, I'm going to move towards them. And then finally, if the player is detected and the player is within range to do some kind of attack, then the AI will do its attack action. Fairly simple. Again, these are relatively automated behaviors. The player really only interacts with these in the sense of like how close they are to enemies. But there are, player activated behaviors all over the place. This is, how players act and control their character within the system. And again, looking at it with a little bit of complexity, there's a game called Trine. It was popular several years ago as like a 3-player kind of co-op game. But all of the characters had different behaviors. Certainly they could all do similar, like the basic movements, like they could all run, they could jump, they could collect items, they could swap weapons. But each of the individual class had specialized behaviors. So the wizard could make blocks that other characters could stand on or use to navigate different parts of the level. The rogue character had a grappling hook that allowed them to cross larger gaps. They also had a bow that gave them access to a ranged attack. The knight character had a sword, which was kind of like the melee attack in the group, and they also had a shield that let them block projectiles. And so the interesting part of this system was like seeing how players interacted as all three of these characters at once and used those different behaviors to kind of overcome the challenges within each level. So I'm going to add some basic behaviors to the system that I've started working on. You can see here they are noted in brackets. So I've taken my sword, I've moved it up because I'm going to need it up here a little bit later. I've given it the behaviors of, equip and unequip. I can put the sword on and take the sword off, sure. I've given my human the behaviors attack, defend, walk, and run, and I've given my monster attack, defend, and breathe fire. This monster, in this case, is immobile, it can't move, but that's how this system has been designed. And we're starting to see, you can kind of put the pieces together now. You probably could when it was back to objects, but whatever. We can almost see the complete system here. Right now, this is still just a bunch of stuff. It's a collection of objects. In order to make it into a system, we need to define the relationships between all of these things. Because without relationships, a system is just a collection of things, right? Relationships define how objects interact with one another and provide context for those interactions. And so they can relate things like locations, they can relate things in hierarchical form, and oftentimes these relationships are determined by either a set of rules within the game and within the game system, or by chance, and they can be a little bit of both within the same type of relationship. So a good example here, think about a stack of blank index cards, right? When you have a stack of blank cards, they don't mean anything. It's just each card is a card, whatever. As soon as you take those cards and write numbers on them or mark a suit on them, you've already started creating a relationship among the cards. So a card of 2 is less than a card of 3. We've already got kind of a hierarchy happening here. And depending on how you might alter that, that could change the way that system functions. If you take away the 3 card out of a sequence of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, taking away 3 from that will slightly change the relationship between those cards. And through that will change the dynamics of a system that uses those cards as well. So really, it's how these relationships between objects are defined. How we do that plays a large part in how the system develops and kind of propagates or executes once it's actually set into motion. Now, relationships are a little bit harder to nail down in some cases, so I've also given some kinds of relationships. Hierarchies are fairly easy to understand. Hierarchies are just greater than or less than relationships. And to a point, if I give you 1, 2, 3, these really are just numbers. But by defining a relationship between them and saying, 1 is less than 2 and 2 is less than 3, these objects now have an order. And when you define them as numbers, it's really easy to intuit that, right? Because we've been seeing numbers most, if not our entire lives. But giving order to things can also be applied to a sequence of ABC or character types, so townsfolk, knight, king. And through that, we can define some kind of hierarchy, whether this is damage based or something else, who knows. But understanding the order of different things in a relationship, or within a system rather, through the relationship of how they are ordered, can be useful. So that's hierarchies. Up next, we've got has relationships, and apologies again for those of you that are doing programming stuff. Some of this is going to sound an awful lot like inheritance because we're getting there. So we think of has relationships as relating a group of objects that show that one object is actually contained within another object, because objects don't always exist on the same, not to use the same word, but hierarchy, right? So let's say we have level 2. Level 2 is our object. But level 2 also has a bunch of other objects within it. It's got a spawn point for the player. It's got a goal. It's got checkpoints. It's got probably some trees or props. It's got at least one enemy, and it's got the player character. So level 2 has all these things within it. And again, those are other, may feed into other systems or other relationships. Next up, we have the is relationship. So here's your inheritance. Is relates objects into more specific sub-objects, and so sub-objects will have similar and a lot of the same really properties as the original object. So let's say we're talking about weapons within an RPG or an action game, whatever you want to call it, but RPG is easier, I guess. It's where my mind is right now. So there's all kinds of different weapon types in an RPG. A sword is a weapon. A staff is a weapon. A bow is a weapon. And so all of these weapons will have their own set of properties. Like let's say, when we're talking about any weapon has an attack value, a weight of that weapon, and maybe some requirements for the character to actually equip it, right? Swords, staves, bows have all of these things. They are weapons. However, a sword, a staff, and a bow, they all also have their own unique properties. So a great example is a bow, right? A bow of these three things is the only ranged weapon. So a bow will have, the attack, the weight, the requirements as defined by it being a weapon. But it also has this unique property in that it also has like a distance that it can be fired, whether that's 60 feet or 120 feet or anything like that. And there are other kinds of relationships too. There are location-based relationships. So when we think back to when I was talking about how enemy AI was working, even in that brief blurb there, the enemy's behavior was dictated by how far away from the player it was. And so that location between two objects can play an important role as well. You can look at, as a relationship, the effects of objects that interact with one another. Oftentimes this is like damage formula. So like how weapons interact with armor, how fire affects ice, and so on. And then think about requirements also between objects. Like a door might have a lock, and that lock needs a key in order to actually open for the player to access. So there's all kinds of different ways that you can define different kinds of relationships between objects in a system. And furthermore, within a game, relationships can be fixed, so they can stay the same, or they can be dynamic and change during gameplay. Relationships can also be what we call loose, which basically means that they have some interaction based on their proximity to something else. So this could be like those location-based relationships that we just talked about. And relationships can change based on what the player chooses, or by random chance, if that's something that is built into our system. A really, let's say, simple but complex enough relationship is showcased in the way that the damage formula and the combat algorithm works in Warcraft 3. And so here we've got a little bit of math, right? Base damage. So to determine our maximum amount of damage that a character can do, we have this handy math formula. So an object would have a base damage, a target would have some armor value, and then an object might have what's called piercing damage that is not affected by armor, as again defined by this equation. So to get our maximum amount of damage, we would say we take our object's base damage, subtract the target's armor value from that, and add any piercing damage that we have, and that's going to give us some value, let's say 50 damage that we can do per hit maximum. We also have a rule within this combat relationship algorithm that says the attacker on any attack deals between 50 and 100% of that maximum damage. And so here we have a relationship that is both rule-based and chance-based, like I was talking about before. So the rules obviously come from this damage formula. That's going to give us a number, right? Whatever that number is, 50, sure. And then the chance side is that on every attack, we're dealing some random amount of damage between half and 100% of that maximum damage. So in my example with 50, every swing of my unit's attack would be doing between 25 and 50 damage. So I could get really lucky and deal 50 damage like 10 times in a row, or I could get really unlucky and deal 25 damage like 10 times in a row. And again, this kind of adds to different possibilities and different combat outcomes that are interesting. We can also think about spoilers. We can also think about how areas within games are connected, and I like to harp on this idea of thinking about terrain and levels as objects as well, because I think that they don't fit quite so easily. Like, it's easy to be like, okay, yeah, game object, I get it. But terrain and levels are a little bit more abstract as far as objects goes. So think about, again, how areas are connected to one another. And this can be, you could look at, Metroidvania style maps. I believe this is half of Castlevania Symphony of the Night. So understanding how each of these kind of areas are connected to one another is a relationship. Or you could look at, the relationships between stages in fighting games like Mortal Kombat, where you can, do some special moves or whatever, and that might change the level that the fight is taking place in. Like all the way back on, I guess really arcade, but Super Nintendo Genesis, there was a level in Mortal Kombat 1 or 2 where you're like on a bridge, and it was really cool. There was like lightning in the background, and at the end of the fight, if you defeated your opponent by uppercutting them, they would fly into the air, and instead of falling down onto the bridge, they would fall below the bridge into this like pit of spikes, which is cool and metal, right? Mortal Kombat, yeah. But too excited. But in further combat rounds, like if you did this on round 1, round 2 would take place not on the bridge, but down in the spike pit, because of the relationship between, okay, the bridge is up here, below the bridge is the spike pit. This relationship has facilitated this thing happening, which is quite cool. Anyway, let's go all the way back to our system, since I think you've seen it for a couple frames already. But let's add a couple relationships here. So let's say, first of all, we're going to relate the sword and the human. We'll say the sword is equipped in both hands to the human. Cool. We're also going to say the sword has a relationship to small enemies, where the sword deals double damage to an enemy if they are small. You will note that this monster does not have the property small, so unfortunately we won't see the effects of that. But again, we can use the power of math and say, okay, well, let's come up with our own simple damage formula. Damage is character's strength plus our weapon's attack minus the defense of the target. So here we see, our sword has 7 attack, we got 4 strength for a total of 11, but then our monster has a defense of 2, so that's going to give us, boom, 9 damage. And so, like, now that we've got some relationships in here, this is a very simple system. There are very few objects. There's not a lot of room for possibility because there are very few objects and very few behaviors. But it's still something that can be interacted with, and all of these objects are related to one another now. And I think it's a good example because within games, not all systems are created equally. You have some really small ones, you have some really large ones. Even systems that have the same kind of output. And a good example would be like, here's the game as a system. You can win or you can lose. Even systems with the same kinds of output can be designed in lots of different ways with lots of different degrees of complexity. And to illustrate this, I'm not going to do it in the scope of this video because I'm already 45 minutes. Yikes. But in the future, we'll take a look at economies in games and look at different ways and different system complexities that we can use to basically exchange goods between the player and the game, or the player and other players. But that's going to do it for this video for now. So I will see you later. See you on Friday for class.